I mean, due to the issue I told yesterday. So it will take place in the week after strings over this LaTeX channel. And those who don't know what's LaTeX, you just talk to Banashri or Pavan. Okay. That's the first thing. So that also gives the speaker some time, some flexibility, and also if Partha allows, because it's saying I'm being biased to holography and so on. In fact, you also give your W infinity thing, right? If you want. Okay. So that's the first thing. The second thing is we have to meet over the next ST4. I mean, people have already started leaving. So I don't want to do it on Friday because most of the people, some of people will be leaving by that. So it's either today or tomorrow. So, aaj karte. Okay, so after, I mean, I don't know. So the third session will be probably a discussion session, or if she wants to, or Tanay wants to discuss something, then do. Or we'll briefly meet over the next ST4 around 5:30 to 6 or something like that. And there's also a dinner from 7:30, I guess. Yeah, I'll share the menu. I've got this. Okay, then you can then decide if you want to join or not. Yeah, okay, so that's fine. So let's bring our next speaker. This is essentially our last topic now for this year ST4. So Kajal Singh from HR will be talking on landscape and string theory.
Am I audible? Okay. So thank you organizers for giving my topic a chance, and thank you all of you for voting for that. So, okay. Just a second. Let me know if I write like smaller or bigger, or if I am talking louder or other. So, okay, so before starting the lecture, let me give a brief, plan how it is going to be. So basically, today we'll talk about mainly the motivation for string landscape, and that is introduction to moduli spaces in compactification, or let's say moduli fields. And then we'll do little bit of required, basics, which is little bit of differential geometry, just to recap everything we need. Then in lecture 2, I'll basically characterize the moduli space of Calabi-House, which are manifolds on which string theory is compactified to give 4-dimensional theories. And I'll give little bit basics of type 2B string theory. And we will see if it is not enough, we can have an extra session. And then I'll talk about a no-go theorem, which is very important. We'll see what it is. Then in lecture 3, I'll basically talk about the stabilization of moduli and how it gives rise to basically string landscape. And in the last lecture, if we have time, I'll talk about some models of moduli stabilization and Basics of swampland. Okay. So most of us know that string theory is kind of lives in the hard. Should I remove this? I mean, it will be visible. Okay. So most of us know that the string theory kind of lives in higher dimensions. And when we go from these higher dimension, let's say 10 dimension to 4 dimension, what happens is we get lots of massless scalars, which are called moduli fields. And due to these moduli fields, when we stabilize them, we have like 10 to the power 500 standard model like models or in 4D. So going from 10D to 4D, we get these many number of basically solutions which look like our standard model. And this is basically what we call string landscape. Okay. Now to see how these moduli fields arise when we do a compactification, let's take some toy examples. So first of all, let me tell about this Kaluza-Klein compactification. That is the way we compactify higher dimension to get a lower dimension theory. Okay. So let's say we have a scalar field in 5D, which looks like R4 times S1. So if the coordinates of these 5 dimensions are x, which are like x0, x1, x2, x3, and last one I'm calling x5. I'm skipping the x4. And the x5 is kind of compactified on a circle. The action which we take, for example, is the simplest one. It's massless scalar field. So it's just half ln capital phi and then phi. And since the fifth dimension is kind of compactified, what we can do is we can expand this capital phi, which is a function of all 5 these coordinates, into Fourier series. So kind of capital phi of x, we can write it as going from 0 to infinity phi n of y times e to the power I n z by r. So now I am taking x to be xm to be y mu comma z, where mu is going from 0, 1, 2, 3 and m r.
So does this require that your geometry has isometry?
Yes. Yes. Okay. So when you do that, what we will see is that the equation of motion for this scalar field, we can write it as following. So and then this modes will appear as kind of mass in the equation of motion of this field. Sorry. Yes.
And now you are writing that field in this way. So that z coordinate is?
The fifth coordinate, which is compactified. So
Okay.
the xm, sorry, it's m, capital M, which runs over this 0, 1, 2, 3, 4, 5, which is,
That's the equation of motion.
yes. When you just simply put it into the original equation of motion in 5 dimension. This one, you get this. Okay.
Kajal, what about the fourth index? Is this the fourth index?
No, I'm just skipping for like, yeah, this is the usual 4D we take. And just to denote, this is a fifth.
Okay.
Just to denote, it's fifth.
So compactification, I don't know anything about string theory, but as far as I know, so if you need to go from 10 dimensions to 4 dimensions, you need another 6-dimensional space.
Yes.
So this is like, why is this 5D, not 6D?
So this is a kind of a toy model to give you motivation for. In next lecture, I'll do the type 2B string theory. We'll be compactifying from 10D to 4D. Okay. Okay. So, okay. So you see that initially we had kind of massless scalar in 5D, and now after compactifying on the 5th dimension, we are getting kind of massive scalars and a massless scalar. So now the action, which is the 4D action, will look like the 0th mode of the expansion, the kinetic term for that, and then all other modes which have a mass. Okay?
This everywhere it's M, right? Del M, phi M. Del M.
Sorry, yeah. So this is M, capital M.
No, you started with M, so M runs from 0 to 3. 3, 1, 2, 3.
No. Okay, so this M index is 0, 1, 2, 3, and 5. So we can take this to be 4, just to denote that, I mean, the 5th dimension is compactified, I'm taking it to be 5. I'm skipping this 4. Okay, if we are fine so far, then the action in 4D will look like this. Now you can see that there is a kind of.
Are we taking N to be positive?
Sorry?
Are we taking N's to be positive, only positive?
Yes.
Why is that?
Uh,
On the other frequencies. The mass is proportional to N square, right? So
yeah, but.
but the mass term is proportional to N square. Yeah. That's okay. But do you get 2 modes per mass or not?
Let me think about it. Okay, I don't have an answer right now. I'll think about it and I'll let you know. Okay, so yeah.
And you're saying like this is surface is right versus left. How do you show it? You're taking only one of them. Maybe there's a delay.
Okay. So these MNs are basically given by N over R. Maybe this is the reason. So yeah, because okay, I'll think about it and maybe tell you later or in next class to everyone. So when we compactify the extra dimension, what we say is that this R should be so small that we will not be able to detect in the lower dimensional theory. So for example, let's take R to be around Planck length. Then this masses of non-zero modes will be around the Planck mass. And by this logic, what we will do is, in lower dimension theory, we will only look at the 0 mode, because These higher modes are kind of integrated out for the energy scale that we are concerned. So in lower D, we only focus on the 0th mode of fields. Okay.
I'm sorry. Can you tell me why? Can you do this? Mn equals to n by r.
So this looks like when you substitute that mode expansion in this action, okay, you'll get this thing, okay?
Yeah, that's fine.
So this looks like mass for the nth mode, right? And when you compare from the kind of, when you compare both putting that and this equation, you'll see that Mn is kind of n by r.
Okay. So I see from the equation of motion you're thinking that.
Yeah. It's like a mass to the non-zero modes.
After we integrate all the massive modes, we
Yeah.
don't have information about R.
No, we have.
R is appearing in the coupling reaction.
No, we have, yeah. So, yeah.
Why do you have a mass term in positive sign?
That is how we write, na? Mass term.
Minus 1 by generally Klein Gordon field is some kinetic term minus 1 by 2 square some square. Is this
I mean,
utilized?
huh?
Is this
Yeah. So, yeah, depends on how, what metric you're. Right now, I think it's, yeah, all plus. Okay. So now when we are focused on only the 0th mode of higher dimensional fields, let's yeah.
So you are discarding this massive modes for this reason, but then the action also looks to be. Why is the action still the limit?
Sorry,
The limit r tends to 0.
Yeah.
The action also seems to go to 0.
Yeah.
But we are saying that we are keeping that, but we are not keeping the massive.
We'll see that we can't take r to be 0 or to infinity. We need r to be some finite and small, radius. That is the kind of whole point of this compactification. Okay. So let me, I'll write it here. So now let's go to a toy model, which is little bit more general, and we'll see how it will relate to later. So let's take pure 5D gravity. Yes?
So the compactification is complete now, is it?
No. This is kind of just to motivate that we are only looking at the 0th mode when we are doing the compactification of higher dimensional field. Okay?
In what sense? So you just substituted that. Is that equivalent to saying that you are looking at only the 0 mode? What about the partial files? Partial filing.
Partial files?
The
They are heavy modes, na? So when you go to lower dimensional, which is kind of a low energy, let's say if you are looking at TeV scale or something like that, we'll integrate out these heavy modes, and only the light modes will stay.
You mean in the partition function?
Yeah, kind of, yeah.
Okay.
Yeah. Okay, so the action for that is M3Q by 2, and then I think d4x dy square root of minus g5 and the 5-dimensional Ricci scalar. Okay, so I'll bring those notes. Yes.
So, in the whole compactification, if I understood correctly, what you're saying is that I have some fields which have mass gap, and then the zeroth mode does not have a mass gap, and your energy is always below
Yes.
the mass gap of the theory that
Yes.
you're looking at. So, if you have many fields, in principle, you can have many massless fields, and
Yes.
you look at only the massless sector of the.
Yes. So that is what we will see now. Okay. So we are. It's 5-dimensional metric.
Now you shifted to the Lorentz signature, right?
Yeah.
You have
Yeah.
a
Yeah. Yeah.
minus G5.
Yeah. Yeah.
So it's not Euclidean anymore.
No. Okay. So let's say we parameterize our 5-dimensional metric GMN as this G mu nu, which is a 4-dimensional metric, and then some fields square P y square A mu, and then when we do that, and yes, it is full 5. So, okay, so M and N are basically given by 0, 1, 2, 3, 5, which we had originally, and mu and nu are again 0, 1, 2, 3. So this is the full 5-dimensional metric, and we can parameterize it in terms of 4-dimensional metric, a vector field, and a scalar field. Okay. So when we use this parameterization and kind of compute these quantities here, we'll get a 4D action, and that also focusing only on the 0th mode of these fields. We'll get S to be some coupling sitting here, and D for X square root of minus G phi square P. This is 4-dimensional tricky scalar, and then we have a kind of a abelian gauge term and a kinetic term for the scalar field. Okay.
So can you just motivate these answers? I mean, I have some. I mean, suppose I have a flat geometry of this flat Minkowski pipe, right? Can I take this kind of answers? What is the form of the?
I mean, you can take, but you will have to impose that R is 0 in 5 dimension, kind of. So that will give kind of constraint on these fields, how they will.
I mean, I can think of like I have a rotating kind of a geometry. Okay, then I can uplift that to a family of geometries through these answers, right? But for example, this A mu term, these cross terms.
Yes.
These are like this curve kind of geometry when you have this fifth dimension and there's a cross term kind of thing, right? But suppose I have a perfectly diagonal matrix.
Yes.
Can I choose this kind of an answers there as well?
There you might have to put extra condition on this matrix being traceless and all that stuff. That's the extra condition that you will have to. So
That is.
mathematically, right? But
Yeah. So then R will be 0.
Suppose I have 5-dimensional theory as a solution. Right?
this is the title.
Yes.
Yeah, that will mean that your basic answer is easy.
Yeah. But this is the most.
I mean, yeah, you are talking about when we are taking this G mu nu to be eta mu nu and this A mu's to be 0, and then we have phi to be set to be, let's say, some constant value. That will correspond to that.
So basically,
So
in
that.
general, 5-dimensional metric can be parameterized.
Yes. Yes.
It's very similar to this radial decomposition.
Yes.
Yeah.
Phi direction is like
Now, is from at this point, is it always globally product, or can you have like twists or something?
I mean, you can have, but the vacuum solution should be kind of global product.
I see.
Yeah.
But in principle, you can allow
Yeah.
for twists in
Yeah.
the compactification.
Yes, yes. Okay. I'm writing like using the board.
Once you do this, right, now you have gravity and so on.
Yes.
How do you fix the size of the compactified cell?
Yeah, that is kind of the problem that the moduli fields are. So phi is like a moduli field. You cannot fix it from this, action itself. So all values of R are kind of solving the 5-dimensional, Einstein equations. So that is.
Here the size of 0 mod of phi itself is besides the size of the cell.
Yes, because it is related to the square root of G55 and kind of. Yes.
For the scalars, there's no massive term for the scalars, so you have thrown them out here.
No, so the 0 mode, if you remember, didn't had any massive.
So you have dropped
Yeah. So there is 1 0 mode. I mean, you can have those massive term, but when you go to the low energy, you are kind of integrated them out. So you have only massless scalars left.
But that will, gauge field will probably never have a massive term, right?
No.
That's always massless.
Yeah.
Scalar.
In 4D, you can't. I mean,
It's
it's like U1 gauge. So.
So the phi that we are using here, that is like after that compactification part, that only the massless sector.
Yes, yes. You have integrated out the 5th dimension that will go into the coupling here, kind of. So.
So you have also integrated out some massive vector.
Yeah, you can think of it like that. So only the 0th mode are kind of in this action, which are massless.
There are also massive vector fields.
If you impose the kind of symmetry in higher dimension also, then there will not be any massive vectors, I think. But in general, I think you can have.
In general, dimensional reduction will never produce m square anyway, can it?
I mean, can't I just write some modes for these values?
Yeah.
Like I did for the scalar second to the same. Like mu by k mu n to the power.
I think it can produce. So you can have massive vector kind of thing.
Did
Yes.
you say that mu is not a function of the fifth coordinate?
Yes. This mu is not a function of 5th coordinate.
Only if you
function of fifth coordinate.
no,
Yeah, I mean.
the massless massive thing. Only if it's a function of the fifth
Yeah.
coordinate you can generate massive thing. So if you just impose by hand, then
Sorry, but this compactification doesn't it necessarily require
you can say
that
things like
Sorry, what I
Okay. So this compactification doesn't require that there is an isometry along the fifth direction.
sorry.
This compactification scheme doesn't it require you have isometry along the fifth direction?
What do you mean? Like you mean G mu nu? I mean that.
This 5-dimensional metric, does it not? Is it not necessary for that metric to have an isometry along the fifth
That's
direction?
right. So you're saying G mu nu is not a function of x, right?
Yes.
So I'm saying the same thing you impose for that. That's how I think we get this metric, but I don't know if there's a reason why you should do that in general. Like
But the
But there is
massless
some-
vector is independent of that.
those.
Yeah.
That I
The
agree.
massive fields will have that dependence on you integrated.
But when she did for the last time, this scalars field has this massive nodes. There she also didn't say that metric has any dependence
So
on
No.
the metric was fixed, right? The background was fixed.
Yeah, whole. Yeah.
Full fields can depend on the fixed coordinate.
This is dependent on the whole 5 coordinates. But when you kind of parameterize and take the 0th mode only, so these fields, let's say this is only the 0th mode kind of field, so these are kind of independent of the 5th dimension here. So
Yeah, because the mu probably lives in this 4th-dimensional space.
yes, yes. Yeah.
So you earlier you had a Kaluza-Klein thing that you were describing for the free field. Now is this just that in this new action?
Yes.
Okay. So and you, as I understood from the discussion, is this metric any 5-dimensional metric can be written in this form.
Yes. You just count, number of components of the 5 dimension and corresponding to the.
And then you just substitute it
Yes.
in the R.
Yes.
Okay, fine.
Also, the dependent of the full metric on the fixed coordinate, will it
Yes.
always be in that form, like will it be the Fourier expansion form, or can it be some other dimension, like some other dependence?
That's the statement of isometry, right? This e to the power I.
What is the prime any function in terms of the bounded set of this?
Isometry is a transformation.
You can do it for
Yeah,
any
but it's understandable. I get it that you rotating around that direction, and so metric doesn't change. So in that sense, yeah.
Yeah, it is. So when you're doing on the S1, that is kind of like a. Does that answer? I mean, is it okay?
So what are your dependence on the G-mean region? So what is it? It's still like a e to the power I kind of thing, right? Here.
Mm.
Even in the 4D metric. No, I mean GML. So when she's plugging in the Einstein.
So just maybe for simplicity, if you assume that it's isometry, you get this directly. Okay, where you may have if you assume that none of them depend on xy, you get this directly. If you assume that it does depend, then you will get massive modes for all the fields,
Yeah.
which is anyway integrating over.
Oh, okay.
Okay. Okay. So these parameters, which we had kind of the 5-dimensional Planck mass, so MP5 is related to this 4-dimensional divided by the kind of the volume of the compactified thing. Now we can have a different kind of moduli field as well. So if we take that was kind of a solution for this. Yeah. Yeah. Okay. So we can also have a different kind of, moduli field, which comes from compactification of the gauge fields in higher dimension. So let's say we have a theory like some, U1 gauge theory. So there is 5-dimensional coupling sitting here. And we have this field strength. Okay, and then we do the same thing where y is compactified on a circle, and you can write your gauge field as capital M as kind of a mu, comma 5, and you can check this that in this case also, following the same argument, we'll get action, which is a 4D action. Okay, you can find the relation between this G square and G5 are related to factor of volume sitting there. So this you can check. But for our discussion, we'll be only focusing on the moduli fields which arise from the metric of the higher dimensional theory. Okay, we'll not be talking about these. Just for completeness, I kind of. So. I took a pure gravity theory in 5D, okay. Then we kind of parameterized the 5-dimensional metric in terms of these 4-dimensional fields, and then we got that theory, and we see that there is a kind of a moduli field here, which is a massless scalar sitting here, and related to the 5th component of the metric, which kind of fixes the volume of the compactified dimension, okay. That is one kind of moduli field. Another kind you can have from compactifying the gauge fields in 5 dimension. So that will give you kind of this. So there also you have a massless scalar.
Okay, 5 to 4.
Yeah.
In this case also we are using a flat field.
Yeah. I mean, when I don't write G basically, then we are kind of using the flat.
When you write phi, right, you mean mode phi, is it?
The 0th.
But no, I mean mode phi, right? You mean the absolute value of phi, right? That's what you mean by phi, right? Because the metric answer was phi square and you couldn't probably.
You're saying whether you can
Ah.
get a complex scalar field in this way?
I'm just saying there's no. This seems to be invariant, and I mean not invariant under phi goes to minus phi, but the metric answers is and the phi should have come just from root G or something, right? Which is the absolute value of phi.
Okay.
You're saying the three-factor phi.
Yeah.
I mean, I shouldn't have
Okay. So you can always scale that, I think. So G going to, let's say, some either G over phi, something like that. When you scale that, you don't need that constraint. It's like kind of while scaling you do.
One more point. Suppose you start from an action in flat space,
Okay.
higher dimension action, then you do this compactify, you arrive at this. Now if I go for if we go on shell for these fields, suppose I integrate now, then this term looks like a cosmological constant kind of term, right?
Which term?
I mean, this if I go on shell for this f and this phi,
Okay.
so then this term is like some r minus lambda kind of term, which is like the action in anti-de-Sitter kind of thing, right? So I start from an action in flat space, I do this, I arrive at 0. Now I can go on shell for this field f and phi, right? And if I put it back, then the only dynamical part is this gravity. The rest of the fields are like some on shell value. So then this action looks like action in anti-de-Sitter space, right? The remaining terms are like cosmological constant.
But this you would have said for flat space theory also, gravity plus light plus scalar. You would have just said the same thing, right?
No, I'm saying that
So-
I'm starting from a flat space thing, but then I come to lower dimensions. She has started from just basic gravity, right?
Yeah.
Even flat space may gravity plus light plus scalar.
No, suppose I don't have light plus scalar. Suppose just square root G R kind of thing. You take these answers there, you come down to lower dimension, you have all these things.
No, his question is you can ask the same question even in flat space. I just have normal flat space metric coupled to scalar field. And then by your logic, I'm saying that by your logic, I can just set phi to some background value. And then I started with something sort of flat space and now I get cosmological constant.
But the whole point is that you cannot set phi to some background value.
No, I can. This is my action, right? I can
Yeah.
always solve for the equation of motion because this JT kind of thing is kind of it arises from there. It comes from so higher dimension thing. Whatever addition field you get, you have to go on shell. Then it becomes like a JT kind of R minus 2 lambda with some delta term.
Okay.
It looks kind of similar to what Madhu was talking yesterday, right? At the horizon, you fix the value for extreme values.
No, there is no horizon. I mean, I'm not talking about what my geometry. My geometry is perfectly dynamic. I'm not doing any geometry.
I mean, it's not always possible for you to just set a field on shell. Like
Yeah.
I mean, only in certain conditions can you set. Either they're massive, then in principle you can sort of, they're slowly fluctuating and this is highly
So I'm
fluctuating.
coming to the point basically that since we know that all values of R will solve this 5D Einstein equation, that means that we can arbitrarily choose any values for phi, right? I mean, kind of like a continuous spectrum of these fields phi, and that so okay, let me just write. So let me just go ahead, and if we don't have an answer for that, yeah. So I think you'll get an answer. So what we got from this 5D toy model is this, that the 5D metric kind of turned into a 4D metric, and we have one gauge field which is abelian, and then we have one massless scalar which is phi. Okay. Now the volume of the compactified direction is maybe given like dy square root of this g55, and that is kind of related to this field phi we have. Okay. So, okay. Yeah. Let me just sorry. Okay. Sorry? First order formalism. I don't understand the question.
Basically, I'm thinking of, instead of crystal symbols, think of spin connection and think of gravity as coming from derivative of spin connection.
Okay.
So then you have like new variables, the additional redundant degrees of freedom, some additional gauge geometry and all. Whether he's asking whether you can still compactify.
Yes, yes.
I think it should still be possible.
Yeah, I can do. So we have a massless scalar, and the problems associated with this massless scalar are following. So we have some problems, which are, first one is that this phi is kind of coupled to this gravity. Sorry, the last, I erased that part, right? So here you had square root of minus g and then del phi square term sitting there. So that is kind of giving us a, in low energy theory, if you think about the phenomenology, it will give you a long range force. And since we already know that there are only 4 forces, this is kind of giving you kind fifth force. We don't have any evidence for that. So this is one reason that we need to kind of stabilize a phi to give it either a vacuum expectation value or maybe give it a mass. And the second problem is that the volume is not fixed if phi is not fixed. And that is a problem because we don't want extra dimension to show up in lower dimensional theory. So we need to stabilize the volume where we have the effective field theories in control. And yeah, so it is kind of not zero, not infinity, somewhere in between where we have kind of all the couplings such that we have a control on the effective field theory. And the third, which I have not shown here, but in generic theory, we can have a coupling with fermions of these moduli fields. And when you don't give a wave to this moduli field, the mass of the fermions is kind of not fixed. So you can think of it as, the okay, so when you have, so when you have, fermionic fields in theory as well, so you can have a, Higgs-like coupling coming in when you compactify. Only different is that the Higgs, the vacuum of the Higgs are related by the symmetry, and this is kind of the different vacuum expectation of phi are not related by symmetry, kind of. So they will give rise to different kind of theories in 4D. Okay.
So this lambda is some new coupling?
Some coupling, yeah.
Sorry, but the coupling is coming from the size of this additional direction, right? So
Yeah. So far,
is there more than one coupling?
I mean, in principle, you can have, right? in principle, you can have more than one coupling, right? Because see, we had like a 5-dimensional.
Additional coupling
Yeah.
theory that is
Yeah,
but
yeah.
suppose I start from only just Einstein gravity.
No, then you will not have such.
Fermions.
Then you will not have such.
How will you get fermions from Einstein
No,
gravity?
no, no. My theory is of solution to zero.
Kajal, how is this? What is the reason for calling it a force?
Then we have to.
So it's kind of naive way of assuming. So if you have a massless field, so the 1 over the mass of field usually gives the range of the force we have. So massless 1 over 0 is kind of long range, which is.
Okay. So why one has to interpret it as a exchange particle for a force? So you're thinking it as like it's a photon corresponding to electromagnetism, graviton for gravity.
Or maybe the W bosons, kind of that kind of thing. So
Yeah. So why does the scalar have to be associated to a force?
it is coupled to gravity.
Isn't it more like a dilaton?
Yeah, dilaton will come. So.
No, I mean this pi r kind of okay. I mean,
Yeah, it's like that.
When you dimensionally reduce that thing, so phi coupled to
but that's it.
and that means
That is.
in all the diagrams you'll have to include phi. Manish.
Sorry, yes.
Yeah. So the thing is, phi when she wrote down that dimensionally reduced action in the first part where she compactified the metric, 5-dimensional metric, in the 4 dimensions in the action, you had a term which had F mu times phi. So from there you know that this phi will mediate. I mean, it will appear in the interactions between.
Okay.
And because
Yeah.
it is massless, it's long range.
Only after you give the wave to phi, it will like, dilaton wave is kind of G string, right? 1 over that. So.
and also I don't understand this point. So initially we were throwing out the massive terms, right? So now where is this mass number coming from?
No, it's okay. It's more like kind of a motivation to why we need to fix this phi, because in more complicated theory, this kind of coupling can arise, and when you fix phi to some wave, that looks like a mass field of this psi. Like originally, we also had massive scalars, right? So that kind of thing. But yeah. Okay, so we saw 2 kinds of moduli so far, and we'll only focus on the geometric part, which is moduli fields arising from metric of the higher dimension. And
Any specific reason for this, like
why we are focusing on?
the moduli coming from the metric and not.
I mean, usually we start only with gravity, right, in higher dimension. So in string theory, those moduli are only kind of mainly relevant for. So if you take other moduli also, you can kind of complexify these fields and taking the other moduli into it. So you can write phi plus some I times, let's say, phi prime, which is coming from the other type of compactification, and then stabilize the total thing. Yeah.
When you say it's not fixed, what do you mean?
It's not fixed means we don't have a potential for it. I mean, the potential is kind of flat. All values of phi.
So volume is not fixed
Oh.
and mass of fermion is not fixed. So it can be anything.
Yes, it can be anything. It is not fixed.
You just do whatever. You can put any value.
Yeah, that we don't want. So we need to fix this thing, right?
Volume of what actually? I missed that.
The high, I mean, compactified. Okay, so let me just write. Dimensions or directions, whatever you want to say. Okay, so now little bit.
Equality is coming, but V55.
Sorry.
That equality. Last one.
Yeah, the parameterization we chose for the metric, from there we can write the square root of G55 is kind of. phi, right? If you remember, we had kind of some g mu nu plus some a mu a nu, some a mu sitting here, and the fifth component was phi square. Okay, so now since we compactified only on one dimension, we had kind of one moduli field, but when going from 10D to 4D, we'll have multiple fields, and to stabilize that we need some non-trivial topological objects. So I'm just telling the story right now. We'll see what these objects. Yes.
So what is the problem in fixing some value after everything is done in phi?
Sorry, I mean.
Why can't we fix phi?
So phi is massless, right? So you cannot give a scale to it, okay? And also there is no potential for phi. So basically, if you have a field, you have a potential for that, and some minima you choose, right?
Okay.
So here we don't have such potential. Okay. So there is no minima. All values are kind of equivalent. Okay. So okay. So let me just write. To stabilize the geometric moduli, which are kind of related to some topologically non-trivial things. We'll see these in next lecture, maybe, or next to next lecture. I'm just kind of giving the idea how we stabilize these moduli. So yeah, these are related to some non-trivial topological objects, and to stabilize that, what we are going to need is a flux which is given by this some general definition of flux. So it's field strength, and over some some manifold of the compactified, which is also and these basically the submanifolds, non-trivial, let's say submanifold here, are directly related to these moduli fields, and we will see how they are related. So to stabilize the geometric moduli, we need some kind of flux going through this non-trivial, some manifold, and the potential which will be generated by this non-zero flux will look like some. Let me not write MC. M is the total manifold. So let's say capital X, which is a kind of. So M is some R4 times X. Okay. So this will, we need kind of a potential which will look like this. Okay, because the G is sitting here, the geometric moduli will kind of be coupled to these field strength, or at least some part of it, and we'll see how this will generate a potential when we go to the lower dimensional theory, and how we stabilize the moduli using this kind of term in the potential. Okay. Now the key factor is that in some generic manifold, which is X manifold, let's say, this C are, we have large number of choices of this submanifold C. Okay. And given this large number of choices, we can have different expectation values of these moduli fields phi, and that in principle give rise to different standard model like looking model in 4D. That is kind of giving a landscape of 4D models. Is that okay?
But the field strength is unique, so then doesn't have a lot of options.
Yeah, field strength is unique. We'll see.
Can you give some examples for this?
Right now at this level, I don't know really. So it's like maybe some non-trivial objects like let's say you have a monopole sitting there, then this will be kind of non-zero in that case. And okay, right now I don't have a neat example, but okay. So we know that we need to stabilize the moduli, right? And to do that, so we are only focusing on the geometric moduli, and we will see these geometric moduli are related to some non-trivial topological objects in the compactified manifold, okay? And to for that, we need a non-zero flux. We'll see why I'm saying we need a non-zero flux here. That is given by some field strength integrated over some submanifold of the compact X, yes, the compactified manifold. And then if we have that, we'll generate a potential for these moduli fields, which looks like this. Okay? Sorry? Yeah, sorry. My handwriting is not kind of. So this is a 4-dimensional potential scale. Yeah, kind of. There will be whole potential, but this moduli part will be. Yeah. Okay, so if we are okay so far, I'll go and do the second part of today's lecture, which is kind of giving a recap of all the concepts in differential geometry. Yes, yes.
What did you ask?
I asked, is this what is called flux compact?
There is non-zero flux, and we are kind of compactifying in presence of non-zero flux. So that is called flux compactification.
And where did Kaluza-Klein compactification end?
It ended, right?
I mean, yeah, I didn't realize when topics changed.
Oh, sorry. Oh, Kaluza-Klein was just up to that scalar part we did. So 5-dimensional scalar, it was just to kind of say that only we are looking at the zeroth mode of the high-dimensional field. So that is the kind of whole idea of Kaluza. A toy model was to introduce these moduli fields, that there are some moduli fields when you compactify from higher dimension to some lower dimension.
I thought even there you were using that kind of machinery that I asked you, but I think maybe I confused you.
Sorry. Okay.
Yes, okay.
So what guarantees that the potential have a minima kind of that? I mean, does it
Guarantee? No. But we will see some models which will, like KKLT you may have heard. So those kind of models give you, a potential which have a, let's say, ADS minima, or you uplift to DS. I mean, not all models are successful. Yeah, little bit. Sorry?
This is only way we know how to generate these potentials in the novel by putting a flux in the.
Yes. Because of the no-go theorem, maybe I told so there is a no-go theorem. If you don't have some non-trivial flux sitting there, you will not have a potential for these fields.
The no-go theorem is a physics theorem or some maths type of theorem?
It's physics.
No, I mean, is it some geometric theorem that if you have any two forms, something like this won't happen, or is it some dynamical thing like?
No, some dynamical thing. So maybe it will be little boring part of today's lecture, but we will see. Okay, so I'll introduce a P form which is in, let's say, D greater than equal to P dimension, is a totally antisymmetric tensor field with its components having p indices. So p indices component, what we usually call tensor objects. Okay, so I try to write lower and bigger. So for example, let's say we are in d equal to 2, then we can have a 0 form, which is just a scalar field, and a 1 form, which is kind of, let's say, u of x dx1 plus some v of x dx2, and we can have a 2 form because we are in 2 dimension. This is the highest form we can have, which is kind of this dx1 wedge dx2, where this wedge product is defined to be antisymmetric. So it's dx1 dx2 minus dx2 dx1, and this is kind of the reason that this has to be totally antisymmetric. If we go to the higher forms, then in all indices. Okay. Now, once you have a form, you can list some properties of it. Let me know if you kind of follow. So you can define an exterior derivative, which I'll denote by D, which takes P form to a P plus 1 form. Okay. This is kind of space of the P form. By lambda, I'll denoting the space of forms. Okay. So lambda P is space of P form, and it is P plus 1 form. So if we take, let's say, f of x, then D acting on f of x will take us to del fx del xi dxi. Okay. So it's 0 form going to 1 form. Okay. Now, an important property of this exterior derivative is that when you act twice it on any form, it will give you 0, simply because of the reason that these two will give you kind of symmetric double derivative, and the wedge product will give you kind of antisymmetric. So symmetric multiplied with antisymmetric is kind of giving you 0. You need to act it on something, right? It's an operator.
Yeah, it's an operator. D square is equal to 0. That is what the pointer lemma says, irrespective of what happens, whether you write omega p or not. Because by default, you will act on p. So D square is 0. This is what pointer lemma, as far as I am.
Maybe.
I mean, you can conclude from this that D square
That's true. But I mean, in any equation, you'll always have D square on anywhere, right?
P is any arbitrary.
So the statements are equivalent. Every time you have a D square in any equation, right, you'll have it on acting on something. So I'm saying it is 0 that one.
need to act it on some p and D square is
Okay. Now, we can define a duality operator, which is called Hodge dual operator, which in D dimension maps the P form to D minus P form, and the mapping is kind of defined by this. Let's say we have dix1 wedge up to dx equal to square root of minus g times d minus p factorial I1, I2 up to IP, then we have IP plus 1 to ID, and this is okay. And when you act it twice on some, let's say, general form, it will give rise to a sign depending on what is your dimension and what form you are taking. Okay. And also, I'm just listing the properties here. So, given two forms, they have this property that you can kind of swap them in d dimension.
What is the superscript of Vx?
P plus 1 to ID, I mean IP plus 1 to ID.
IP plus 1.
Yeah.
And but in the epsilon there are all the indices.
Yeah, yeah. So this will be upper index, sorry. I1, I2 to IP, and then IP plus 1 to ID. Okay. So yeah, in the epsilon will always have the maximal number of indices, right? Okay. Now, any P form, given that they look like this, we can integrate them over a P dimensional manifold. So a P form can be integrated over a P dimensional manifold, which will denote as sigma P omega P, and that will look like dpx, the component omega I1 omega IP. Okay. Now, given that this integration, we can, sorry? Yes.
It depends only on D, right? It doesn't say anything.
And signature. If you have Lorentzian signature versus Euclidean signature, that sign changes.
What I was saying is if D is odd, it will always be -1, and if D is even, it always will be even.
Signature dependent statement. The Hodge dual the double Hodge dual depends on signature.
Of the metric. But I think in Euclidean, flat it looks like this.
Yeah.
So
I don't know which one this is, whether Euclidean.
yeah, yeah, it's Euclidean.
Here I thought that you can ignore the P dependence in the case, right? You can just do.
Sorry, I didn't hear what you're saying.
If you evaluate D minus P into P, right?
Yes.
Say D is odd,
Yes.
P is even,
Yes.
D minus P will be odd.
Yes.
P
Okay.
is odd, D minus P will be even. So D minus P into P is
Um,
some even odd number. That is if D is odd. And I think if D is even, this product will be even. So I guess the P part you can ignore.
I don't know. I don't think we can ignore this thing. There will be some forms which will change the sign and some will not. Okay. So let me define the inner product. So if we have two forms which are both are P forms, then the inner product of these forms are defined as integration over whole manifold, which is a d-dimensional manifold in this case, and this product where we take the Hasse dual of the second form and kind of wedge product with the first form. So this is kind of a map which takes a P form to, space of real numbers.
Depend on compact manifold. Because
Not.
if you want the inner product to be symmetric in alpha and beta, then you have to show some. Is that not true?
I think if you want to show that, then it should be on compact manifold, right?
I'm not.
I don't remember exactly.
Yeah, I'm also forgetting. Like,
Kajal, sorry, can you repeat what was
I
this?
think inner product you don't need
Omega
to
of some.
define D.
Yeah,
you
yeah.
need, sorry.
Yeah. Sorry. Yes.
So you're integrating a P form over sigma P.
Yeah.
And
Which
what
is.
on the right side?
So I'm just, opening up this omega p, which will be like some omega, this component times dx1, dx2 up to dxp. Okay? Then that will kind of look like this when you have. Which? Yeah. So it's like you contract, then you will get 1, 2, 3 up to p, and then it will turn to the volume element of the. Okay. So once we have defined this inner product, we can define an adjoint of the exterior derivative. Okay. Which is, so alpha p inner product with some d of p minus 1 form is equivalent to, this is kind of definition of the adjoint, some d dagger inner product with this p minus 1. So from this definition you can see that this d dagger, what it does is takes a p form to a p minus 1 form. Okay.
This requires compact manifold, right? When you do the integration by parts.
Yes. It will. Yeah. Yeah, some boundary will be required. Okay. And it also follows from this that same example or same property we had for D is that acting twice D dagger on something or D dagger square itself is 0. Okay. Now, given these operators, we can define the Laplacian in this notation. Delta, it takes a p form to a p form and is defined as, in terms of these exterior derivatives, this. When again using the properties that the squares of these will be 0 acting on any form, we'll get it to be this. Okay. And if we are fine so far, I'll define what is called harmonic form, which will be kind of important for our discussion. So a p form, omega p, is called harmonic if delta acting on omega p is 0, and this is satisfied if and only if d acting on omega is 0 and d dagger acting on omega is 0. So, a form which satisfies this property is called closed form, and the similar one will be for the adjoint derivative, it will be called co-closed form. Okay. So, you can see this by kind of computing inner product of omega with its delta omega, and you will see how you will get these things. So, you can kind of check it. So, this is exercise. Use this, the positivity of this, to show that d dagger and d omega both are 0. Okay. Now, okay, so last, or maybe the second last thing in this property is that if a p form, which is omega p, can be written as the exterior derivative of some p minus 1 form, then it is called an exact form. And similarly, if a p form can be written as the adjoint derivative of some p plus 1 form, then it is called co-exact. And the important theorem, which is Hodge, I will not prove this, but it can be found in any differential geometry books. So, if M is a compact manifold, then only this is true. Then we can write any p form omega p as a sum of an exact form, and then a co-exact form and a harmonic form. So, this is kind of the statement of Hodge's theorem. This is the exact part, this is the co-exact part, and this is the harmonic part. Okay. Now, we need two important concepts, which is homology and cohomology. So, I will first talk about homology, and before doing that, let me just maybe give one picture. So, we have some two-dimensional disk, and on that, let us say we have this kind of sub-manifold, and we have another one-dimensional sub-manifold. So, let me call this disk C1 and this line element C2. Then the boundary of this disk is basically denoted as del of C1, and the boundary of this C2 are these 2 points, which is del of C2 are these 2 points. Okay? Yes. Yes.
So are there any constraints on this gamma?
It is harmonic, so it has to satisfy this condition. Delta of gamma p is 0. Okay, so we are kind of defining delta as a boundary operator. Now the statement for homology is that, let's say we have this C1 here and we have some other kind of submanifold, which is in this case C3. Then this C1 and C3 are equivalent to each other. That is the statement of homological. C1 and C3. Yes.
If it sounds very nice. So, if I mean, it is regarding the harmonic form, okay?
Hmm.
Suppose if I have a one form, okay? Suppose omega p is one form,
Okay.
okay, and it's closed. So that does it mean that a one form is always harmonic?
Why? I mean,
Like delta of the suppose d omega omega is one form, so d omega is zero. Suppose.
okay.
So does it mean that harmonic form always has so it implies that harmonic I mean one form always has to be harmonic, right?
You're saying
I mean,
you're looking at closed one form? You're saying D is closed one form.
If omega is closed, I mean d omega, yeah.
you are saying that for one form, if we have satisfied this thing, then it is harmonic itself?
Yeah. Because then because if that is the case, then this raises this, I mean, we have to impose extra condition on alpha, which appears in the Hodge theorem, right?
Why? I mean,
You can see, because then omega p has to be equal to gamma p. Then omega, then alpha is. I'm just trying to understand.
I mean,
Sorry, why if
I-
omega is zero, why should the dagger of
yeah.
omega is zero?
It depends on what dimension you are, if let's say you are in one dimension, then that is a sufficient condition for it to be harmonic, because there is no hard form that can, be written as, this thing. Okay.
What do you say, C3?
Okay, so I will tell the, formal definition of homology classes, but just to give you a picture that the statement of the homology is that this submanifold is kind of equivalent to this submanifold. So C1 is equivalent to C3. Okay.
How did you draw C3?
C3 is the bigger disk basically.
So
How?
any submanifold that has C1 in it, is that how you do it?
Yeah, you can think of it like that, or
This looks almost like a homotopy kind of thing, like continuously deformed, something like that.
yeah, you can. I think you can say that, but
They're topologically equivalent, that's what you're saying.
The topologically equivalent
I mean,
for
so let me give the definition. Maybe that then it will be clear. So let's assume that we have a smooth and connected manifold M. Then I'll define what is called a P chain. So a P chain is basically AP and sum over I, Ci, Ni, where this is a formal sum. And Ni's are p-dimensional submanifolds on M, and Ci can be a complex number. So Ci is some complex or real number. If it is complex, then chains are complex, and if it is real, then so on. Submanifold of the M, p-dimensional. So for example, we had here one-dimensional submanifold on two-dimensional. Okay. And then we can define the, boundary of this P chain, which is this delta operator operating on AP, and that is nothing but basically it will operate on the submanifold. So this is boundary of P chain, which is a P minus 1 chain. So this is P minus 1 chain, which is obvious from the example that the boundary of a two-dimensional surface is kind of one-dimensional, and so on.
So this kind of like simply connected with something something like that. I mean, I have come across terms like simply connected manifold. So if the connected means simply connected, or there is some other.
It need not be just simply connected. You can have multiple connected. So I think if you
Genus.
Huh?
Having a genus.
Holes also.
Yeah.
So this manifold takes care of that.
It can,
Yeah.
yeah.
We will see the example basically for, we'll see for torus how it is. Okay. So once we have defined chains and their boundaries, we can say what homology are. So let ZP be the set of all these P chains which don't have a boundary basically. So the boundary of these P chains are 0, and such chains is kind of called cycles, and I'll be using the name cycles a lot in coming lectures, so I'm just saying that. And then we have a set of all P chains, so let's say beta P, which can be written as boundary of some P plus 1 chain, some alpha P plus 1. These alphas are different, so just some notation. Okay. So when we have these two sets, then the P homology of M is given by this ZP modulo B.
So when you say that the set of all, if dou AP is 0,
Yes.
it need not mean that individually all the dou ni's are 0. Some in this formal sum somehow they can cancel.
Yeah, it can.
Sorry. No. I'm not asking a question about the set. I'm asking the dou AP equal to 0. Does it necessarily imply, because you haven't been told what the sum is, right? Therefore the dou ni's are 0.
I mean,
No, I'm asking the AP or dou AP.
I think so, but right now I don't have an example which, because usually the examples we take are itself boundaryless and
So
total.
What are the indices I running over?
Oh, so I is kind of running over all the bases of this P forms or P submanifold. So you can have different submanifolds in a M manifold. So all possible patches kind of.
So you're taking like a sum of like lines and some surfaces. Is it like
I mean, yeah, I don't know if we can say it like that, but it's
So
kind
all
of,
of them are p-dimensional manifolds, Ni.
yes. We are defining the P chain, right? So they have to be P dimensional.
So P is less than equal to M, right?
Less than equal to M, yes, of course.
Like if you have a sphere, you can have some manifolds which are again two-dimensional.
Yes.
So you could take any number of them. How would you restrict?
why do you want to restrict?
How would you define a P chain then on a sphere?
So it's like, let's say I have multiple circles.
Yeah.
Okay. So all of them, let me just call them like Ni in one end.
Right.
And then my P chain will just basically be some C A.
You can have arbitrary sort of things. Right?
Arbitrary, up to you. So the question that I was thinking of is, let's say you take the plane, okay, and then I have x less than 0 and x greater than 0, two submanifolds, right? Okay. Whether these bounds, so now individually both the C's are same. Naively you can both have a boundary which is equal to 0. And if I choose both Ci to be the same, do they cancel or do they necessarily have to? In the formal sum.
There can be many more features.
Correct, absolutely.
You're subtracting them.
I mean, it depends on the C's, right? So.
Yeah, but I mean, I think you can get the full space, but how can you subtract two different spaces to get nothing?
That was my question. Whether this formal sum allows you to get.
No, probably
I think it should, because from cohomology it should work. I think.
How you subtract two spaces?
so because otherwise, how do you define this?
I think you can add.
If you can't add or subtract, then you cannot define this formal sum.
Yeah, it
I mean,
is
adding
formal.
might be like composing them together, like putting them together.
Otherwise, you could have just said that this delta n is implying that, but she is saying that only the delta n is existing. That means you can define the formal sum, and it can have boundaries of each of these components, but the total boundary is 0.
Yes.
In this case, do we have any like implicit notion of orientability? Like I'm thinking from the example that Anish was just saying.
No, no.
Half of the plane is going to be
No, I don't think so. Like.
So technically it's over. I mean, if you can avoid those.
Yeah, half an hour I'll need.
Quite some definition.
So, okay, so let me just write, maybe it will be clear for. So we have, let's say, a chain AP which belongs to ZP. Then this will be equivalent to some other A prime P if A prime P is written as AP plus some boundary of, P plus 1 chain. Okay. Sorry. Is it fine so far?
So can you just go back to that example?
Okay.
What are those C3?
Let me think. So, C3 is C1 is the disk which I have shaded kind of, and yeah, in this case I think C3 is also the whole disk which is outside the C1, but I get where you are heading basically.
Yes. But these two have different boundaries.
Yeah.
I think in the example is so if I just naively think of dou C3, that will be the external circle, right?
Yes.
What you mean is probably like is the annulus C3 is just the annulus, and the external thing is non-compact or something. Is that how you are thinking?
They are differing by boundary.
No, I think in this case I should have said like these two circles are equivalent basically because they are related by the boundary of some two-dimensional, some manifold. Maybe I stated it wrong. Okay. Maybe I'll just need 10 or 15 minutes just to, some stopping point.
So we are
Filling the growth of
Yes.
we are summing over.
the camera is working.
Sorry, you were asking?
Break now.
We are summing over all these three manifolds, no? So in the picture it is like all these bounded, like these two circles, like that you are really summing over that.
Yeah, kind of.
So what is the physical notation? Or is it a total like who is putting the circles?
I mean, so I think on torus it will be a little bit clear because then we have two different kind of circles. So that example is just to say what is I mean by when I say boundary of these chains or kind of those things.
So, okay, these circles are chains.
Yeah, one chain, right? Because one dimensional submanifold of total thing.
Okay. And so shaded region is something as well.
I mean, I think I said wrong here. So um, let's say this circle is C3 and this small circle is some C4. Then the statement of cohomology is that C3 and C4 are equivalent because they are related by some higher dimensional, boundary of some higher dimensional manifold. Okay. That example was just to say what is the boundary operator does on.
So you're relating those boundaries.
Yeah. So let me just give the example for torus. If it is okay, we can take a break until it is working back. Yeah, I can. I mean, I'll need just 15 more minutes. So if we just want to do some,
So where is your beta? So in this alpha p prime equals to alpha p plus partial beta.
if I'll draw the torus, then it will be easier. So I'll just explain when later also. So let me just for sake of completeness, we have this torus, okay, and let's say we have a one cycle which is so if I have a different colored chalk. So this is one kind of a cycle here, okay, and we can have another one either inside or outside, okay. So the statement of the homology is these two are kind of equivalent because they are related by the boundary of this shaded area in between them, okay. They're kind of, so let's say if I call them A1 or A and B, then A is equivalent to B because A is equal to B plus delta of sigma, where sigma is this shaded area between them. And we can have another cycle like this, but this and this are not equivalent because you cannot take any other sub-manifold or the total manifold from where you can kind of take the boundary and go from this cycle to the bigger cycle, okay.
So this sounds a lot like topologically equivalent or inequivalent. So do you know why one introduces this instead of just talking about topology? Yeah, I mean, what is the difference? So I could say that the two that she's talking about are topologically equivalent.
Which one? A and B you are talking about?
Yeah.
Yeah.
I can do that.
Yes. I mean, continuously you can deform it too.
Right.
Yes.
So that's not same as what?
No. I mean, the definitions are little bit different. So, like, I think, I don't know if I'm, first homotopy is if you can shrink it to a point, then the first homotopy. If you cannot, yes, shrink it to kind of sphere, then it is second homotopy. So I don't think it is the same thing. So the homotopy definitions are, let's say you take any curve on this manifold or any manifold, if you can shrink that to a point,
Kind of the second
On a sphere, I can.
yeah, on a sphere also. So on sphere you can take, like, let's say we have a sphere. So if you take some circle or some disk here, this circle can be shrink to point, right? So that is the first homotopy. And similarly there also. So you cannot shrink this circle to a point, right? So that is why it's, for torus, the first homotopy is kind of non-trivial. It's S1 cross S1. And the second homotopy is, like, it's like all homotopy, if I am saying. So first is like, I don't know,